Okay, now we are recording, and thanks everyone to join us in the back of our tech talk. And Mauricio is a friend of mine, and he was also my co-supervisor in my master degree. He's very well knowledge about computer science and quality software test of software and so on and so forth. And he is joining us to talk a little bit about his last research. And yeah, thank you, Mauricio. And the presentation is all yours right now. Mhm.
Thank you so much. Thanks, Swelling, for the invitation. Hello, everybody. My name is Mauricio. I'm an assistant professor at Delft University of Technology in the Netherlands. Quick introduction about me. Let me just try to change my slides. I'm originally from São Paulo, Brazil. I did my master's and my PhD at the University of São Paulo. My research was always about empirical software engineering, which is basically trying to understand whether different practices in software engineering work or not by means of science. I also worked for a couple companies, Verifone, which is an American company, LocalWebby, and Alura. I wrote 2 books that were derived from my experience at Kaelum, one on test-driven development, another one on object-oriented programming and solid. There's a new book. I signed a contract a few weeks ago with Manning. This book will be on software testing. I hope you are going to like it. I finished my PhD. I came here to the Netherlands to do my postdoc. After my postdoc, they offered me an assistant professorship. I said yes, and I do a lot of research in here. A lot of it actually is very applied research, which is what I like. And the 2 companies I do a lot of work, and I'm going to mention throughout my talk, is Adyen. Adyen is the largest Dutch unicorn. They are a payment gateway. So if you pay Netflix, Spotify, Uber, a lot of those companies use Adyen as their payment gateway. So maybe if you look at your credit card records, you're going to see the word Adyen there because they are the ones processing the payments. ING is a Dutch bank, a very large one, and they have been modernizing their entire way of developing. They see themselves as a tech company. They do a lot of research with us. And well, my talk is all about the last 2.5 years of research I've been doing, and it's all about machine learning. Of course, my dog loves to participate. And this is a very good moment to talk about it because a few weeks ago, GitHub released the GitHub Copilot. And the idea is you just write some text in English, then the Copilot writes the code for you. And it's just more than, a simple search on Stack Overflow. It understands the code you wrote before, so it can use the proper variables, so on and so forth. And of course, besides all the discussions you see on Twitter, whether this is legal or not, to train a model on GPL code, besides all the bugs that people have found. For example, I saw someone showing that Copilot suggested a drop table or something. Regardless of all those things, you have to agree with me that the technology is just impressive. Just imagine this 5 years from now. Why do we need AI or machine learning for software engineering? Well, because a lot of the problems we try to solve for developers, for example, helping them to decide whether the code has quality or not, technical debt stuff, bug detection, software monitoring, all of those tools, they are mostly written by humans. And what do I mean by that? For example, SonarQube detects God classes for you, right? We don't like God classes. We want to refactor God classes. But how does this work? SonarQube has behind the scenes some heuristic there that basically looks at static analysis metrics. For example, if coupling is higher than this and complexity is higher than that, whatever, then you have a God class. The same for spot bugs, right? So spot bugs has a list of static rules. If the rule matches your source code, then you have the bug. Otherwise, you don't have the bug, right? So those rules are written by humans. And of course, the consequence of this is that the number of false positives is very high, right? Why do developers simply ignore a lot of those? In just a second, let me say a few words to my dog. Dookie, hey. Just because there are lots of false positives, right? So the tool says, gives an alarm to you. You don't like the alarm because you think the alarm makes no sense. Expected, right? As humans, we can see just so much. It's very hard for us to design an heuristic that captures the complex phenomenon that is code quality. 10 years ago, there was this paper, and the paper basically compared source code and natural language, right? And what the paper noticed is that source code and natural language share a lot of characteristics. Source code is as repetitive as natural language. And the beauty of this finding is that then we can basically use everything that people have been using for natural language processing to source code. We can train basically the same models. Think of the Facebook's model that translates from one language to the other. This is today mostly driven by machine learning, right? And we can apply the same things, but instead of the task being codes or a language translation, the task will be finding a bug or suggesting a refactoring or something like that. And this is what my talk is all about today. But just a small remark, I'm not gonna say or show fancy stuff like the GitHub Copilot. That's just another level of fanciness done by a large number of very good machine learning engineers with unlimited resources. What I'm going to show here is that it's more like simpler stuff that you can do. Any company can do. You don't have to have Google's computing capacity to do that, and yet those things can be quite powerful. And just to give you an impression of all the different types of problems we have been trying to solve using ML or artificial intelligence, for example, detecting bugs and a particular class of bugs off by one mistakes. Those bugs are very hard to be found by static analysis. Or let me put in another way, static analysis tools never find off by one mistakes. Maybe AI can help us with that. Refactoring, can we build things that are just smarter than SonarQube to suggest you what to refactor? Log placement. In enterprise applications, logging is a big problem. You need to know what to log. Can we build models that learn how to log or when to log? Anomaly detection, defect prediction. Can we predict whether a class has a bigger odds of having a bug so that maybe the developer can spend some extra time doing code review? Software remodularization, test case generation, system behavior, modeling system behavior, so on and so forth. Folks, I'm going to just turn off my video and my microphone for a second. I'm going to move my dog to another place. I'll be right back.
Okay, no problem.
To another place, I mean the couch, which is just 1 meter away from me, but hopefully he will like them. I see messages in the chat, folks. Feel free to ask me questions at any moment, okay? And in here, I'm making this separation between machine learning or deep learning and artificial intelligence. And the difference here is that in the machine learning part, I'm going to show you how we learn from source code, right? You're going to learn from lots and lots of examples and train a model. In the AI part, I'm mostly using search-based algorithms. So if you're familiar with genetic algorithms, these kind of things, those things are very good. They also work very well. Those things are even closer to production nowadays. You see companies like Facebook and Google using those things. But I'm going to focus on the machine learning part because I guess it's a newer, maybe more exciting if you don't know how those things are applied for software engineering. And I'm going to mostly talk about this. Let me see where my mouse is. I'm going to talk about the first 3 papers here. I guess that's what I can do in the time we have. But of course, you're always free to ask me questions about anything. Let me go to the first one, which is all about recommending refactoring. And of course, everything that I'm going to talk about, those are published papers. You can read the papers if you want to know all the details. We all know what refactoring is. We like refactoring. Empirical research shows that developers see benefits in refactored code bases, etc. Then how do those tools work nowadays when it comes to find code that we don't like, that we want to refactor? As I said before, we basically get some best practice. Maybe this comes from a more traditional book. Maybe this comes from your development team. Then what we usually try to do is to convert those good practices into things we can measure, and usually in a cheap way, for example, by means of code metrics. So let's say complexity or some notion of cohesion or whatever. You put those things together, you define some thresholds, and then your tool will start to alarm you whenever something is bigger than the threshold. This is what every tool does. The idea was initially proposed by Marinescu, and a lot of tools actually followed it. That is great. And to be honest, I even liked this idea. So you see even the paper that Swelling published in her master thesis. And the idea was basically talking to developers, trying to understand things that they don't like, maybe propose a tool that finds those things. But as I said, this all depends on humans trying to come up with heuristics. So let's switch the way of thinking. So instead of us trying to define the rules, let's let the machine learn the rules, right? And so let's try to train a model that will learn what methods you like to refactor, right? So that was the idea of this work. And how do we do? Very simple. It's basically a binary classification problem. So we give to the model a lot of examples of methods that needed to be refactored. How do we know this? Because we really go to repositories, like your Git repository. We look for refactors. So let's say we are trying to train a model that recommends extract methods. We visit your repo, we find every moment where an extract method happens, and then we get that method as an example, right? Just before you apply the refactoring, that's a very good example of a method that suffered a extract method and that the model can learn from. So we get lots and lots of those methods. And then we also get lots and lots of methods that do not need to be refactored. They are good enough, right? So that the model learns basically how to separate between these two classes of things. What types of refactorings? Well, we tried different ones to kind of prove the ideal in a more generic way. But the question is, how do you get these refactorings? Well, there are tools for this nowadays that you just give your GitHub repo, and the tool visits your repo and tells you in this commit, this refactoring has happened in these methods. It's quite a recent tool, actually, from 2018, and the accuracy is just amazing. So collecting data, which is usually a big problem in machine learning, this kind of helps us here because we can automatically collect this data. And that's what we did. And we did this in scale. So we collected around 11,000 projects, 9,000 projects from GitHub, 1,000 projects from F-Droid, 900 projects from Apache, mostly to try to see if those models could learn from projects that are completely different from each other, right? Like a mobile app is definitely different from an Apache library. There are 9 million commits in those projects. We mined them all. We extracted a bunch of refactorings from all the types. For example, there are 300,000 extract methods in those repos. Developers do a lot of extract methods, right? And that's nice. We can learn from those. 1,000 hours of data collection later, what we had was for all the methods that we want to learn from, we extracted code metrics. What types of code metrics? The simplest ones you can think of, from complexity, coupling, complexity, etc., up to basic counting that you can do. For example, let me see a good one: max number of nested blocks, right? So if you have a very deep if, maybe that's a hint for the model that you need to refactor. So we collected lots of those without hypotheses. We just collected the data. We also tried to collect some other types of data, like, for example, things you can get from the repo, like the number of times a class was committed, because this gives an intuition of how much you change that class, so the model can leverage that. We also give different levels of information to the model. And one example is, let's suppose we want to predict a refactoring that is at method level. we give to the model not only the metrics at method level, but also the metrics of the class that that method is in. This is very common in machine learning. You do that because you want the model to learn also some sort of context. That makes sense to me in practice. You as a developer, you usually know where your method is, and you take this into consideration in your reasoning to decide what to refactor. So we just feed a lot of this data to the machine learning models. I'm really sorry, folks. He usually talks a lot, but not so. It's even now the other one that is crying. Amazing. And we just do some basic machine learning there. Nothing fancy. We balance the data sets because the data is imbalanced. We do some feature scaling. We do some basic hyperparameter optimization. And we do, simple cross-validation to be a little bit more sure about the results. Then if I go straight to the results, there's this huge table in the paper. Let me summarize this for you. So the gist is that those models can learn how to separate between methods that need refactoring and methods that do not need refactoring. And the random forest model are the best ones. And they have sometimes an accuracy of 90%. So this means out of 10 times, I ask the model to give me the recommendation. In 9 times, the model is correct in the prediction. Even simpler models like logistic regression, they show some nice accuracy, like 80%. And that kind of shows to me that the way developers decide to refactor is not so complex. Even simpler models can model the phenomenon in a way, right? It's not as simple as the God class strategy we have in SonarQube, but it's also not something very complex, right? Models like that can capture this. The idea of giving the class level information to predict method level refactoring, so this notion of context that I told you, this also makes a difference, right? So those features are very important to the model. The model needs those. That's really cool. Then the next thing we answered was, do those models generalize? If I give this model to you right now, can you use it? Would it be accurate, right? And how did we try that? So we trained the models on the 3 different data sets we have. So we trained it in one data set, let's say Apache, and we tried on F-Droid, for example. There you see that the numbers are not as good as the numbers we had before, but they are not so bad as well, right? Which is okay, which kind of shows that those models, learning from your own data points, that's very good. But if you don't have the luxury of having those data points, if you use a generic model, you will still get some benefits there. This also shows to me, right, that the reason to refactor is kind of global. It doesn't matter if you're developing a mobile application or a library like an Apache library. A lot of the reasons to refactor are the same, right? We all hate long methods, let's say. So that is why I guess that's my conjecture why those models work, because at the end of the day, we have the same reasons to refactor. Finally, the big challenge that I see in this line of research right now, whenever it comes to machine learning, it's all about the data, right? And I think the challenge in collecting this data is to collect the methods that do not need refactoring, because we don't have a data set, that says, those 100,000 methods over there, they're beautiful methods. Let's learn from those. We don't have those. So I had to approximate this data set of methods that are good. What was my idea? The heuristic that we proposed was we get classes or methods where developers were changing, right? They were doing modifications there, but no refactorings, right? So the intuition was people can evolve those methods without needing to refactor them. So that was our, heuristic. Maybe not very good. Maybe it is good. It's pretty hard to know. We need more investigation in there. But I also showed that in the paper. So I said we look at classes or methods that are changed but not refactored, and it has to be an X number of times, right? At some point, I have to say that's good enough. Let me get this data point. So I tried a very conservative threshold at the beginning, like 50. And then later, as an ablation study, we also tried 25, which is half, and 100, which is the double. We, of course, saw variations in the precision and in the recall of the models. So this basically means that picking this threshold is a decision you are going to have to make when training a model like that for you. What's more important to you? Is it precision or recall? Then you decide, and then you train the model accordingly, right? So that was one thing to think about. Our tools are available on GitHub. When I coded this tool in 2018, the tool was far from being perfect, but it's very nice that I have lots of very good master students that can fix my bugs. And Jan got my tool and he spent a lot of time. The tool rarely fails now. What do I mean by fail? Getting data from a Git repo is just a mess, right? If you really try to write a tool that visits a Git repo and does things, you're going to see how Git was not really prepared for this. So things happen. But Jan fixed a lot of these bugs. The ML pipeline is very easy to be used now. We actually just used in one industry partner. We tried in a larger data set. Results are still, they still hold. Our tool, while the data model is a bit confusing, we need to refactor a lot of stuff in there, but the tool kind of works. So you can actually train a model for your company, which is what I'm going to show now, where we actually trained a model for ING. We trained a model on struct methods refactorings at ING. This work was done by another master student of mine, by David. He just graduated. And what we did was, first thing was, we wanted to understand if the source code of ING was very different from the source code of the open source projects that we collected data from, right? I didn't discuss this, but by the way, quality matters, right? And when I collect metrics from the first 100,000 projects on GitHub, that's what we have right now. There's a lot of trash in there, right? Lots of pet projects, useless stuff. I don't know how GitHub is handling this with Copilot, but definitely in my data set, I see lots of data points I don't like. So in real life, once a company decides to productize this, they will have to find a way to collect good metrics. But anyways, we wanted to compare ING's data with open source data, because the assumption behind those models is that the distribution is kind of the same, right? That's if the distribution is the same, then this means the model would work very well in your problem. And we actually show that there are similarities and differences in the way that ING developers decide to refactor. So for example, ING developers, they refactor classes that are usually smaller than the classes that open source developers refactor, right? Maybe because ING's classes are smaller, maybe because open source developers are more, what's the word in English for that? They can resist more and only refactor when something is really problematic. I don't know. The point is, things are a little bit different, but also a little bit similar. So we then conjectured maybe ING deserves a dedicated model, which is what we did. So we collected extract methods directly from the ING code base. And we empirically evaluated which model was best. Random forest again was the best, so an accuracy of 93%. Interestingly, when we tried to do what we call all but one, so we train it on all projects at ING -1 that we removed randomly, and then we trained the model on this, and we tested on the project we removed from the training set. The precision kind of drops, right? That might be because the number of data points is not enough. So I think at ING we had maybe 2,000 data points or so not a lot. But it also might mean that some projects are very different from other projects, even within the same company. And when we were doing qualitative analysis there, we definitely, we indeed saw one project that was really different from the others. The open source model, if we try the open source model at ING, you see that we achieve like 75% accuracy, which is very different from the one that you get if you train on your own data set, right? So the ideal is, if you want to use this model, my suggestion would be you train your own model, right? Do not use generic models. I'm going to discuss more about that later. Finally, at ING, what we did was we were curious to see if the recommendations of the model would match what experts at ING would recommend. So we basically did a blind study where we showed 30 recommendations of the model to the experts. I think it was 20 recommendations where the model said, let's refactor this, and 10 recommendations where the model said, let's not refactor this. The expert did not know, of course, what was the recommendation of the model. And we asked the person, would you refactor this or not? Yes or no? And then why? And then we later compared to the recommendations of the model. And then you kind of see that there is some agreement, right? Some people agree a lot, like developer number 5. This person over here was actually the developer that was closest to the battlefield. So this guy was writing code every day. These other guys are more in a less coding position. So we see a little bit less of an agreement, but it's a bit better. It definitely somewhat matches with what the models are proposing, right? So this means those models are kind of learning something, right? That those models learn why developers refactor. So that was the first one. On refactoring, let me move to the other one, which is about recommending logs, right? Where should we log? Which methods should we log? And this was done by my PhD student, Jean. This work was done together with Ajin. And so let's do it. So we know what logging is about. We want to, as a developer, we want to put those log instructions in our code so that once a bug happens, we have enough information to debug it. And of course, you don't want to log too much because that would make your infrastructure too heavy. You might require too much infrastructure for that. And you don't want to log too little, right? Otherwise, you don't have information to debug. In our industry partner, I don't know the numbers by heart. They double every month or so. But I think when we did this work, beginning of last year, I think they had like 120 billion log lines a month in their logging infrastructure. And that's because they're very careful about what they log, right? So our goal was, let's help developers know what to log. So same idea here, let's learn from code. And what we did was we got all the methods in their code base. For example, this one. This is a fake one, by the way, but enough to illustrate. And then those methods have logs. So if there's a log, we just assign a label true for this so that the model learns that, well, that there's a log in here. But before giving it to the model, we of course remove the log lines because otherwise the model would just learn if there's the log, then you log. That's not what you want. So we remove the logs so that the model kind of learns from the intuition, from the intent of that method. We again give lots of code metrics that are very cheap to be extracted. And the same thing for methods that don't have logs, the same procedure. The difference is that then the label is false, so that again, we train a binary classification model. In our industry partner, the code base is quite large. So they had around 310,000 methods in their code base that are not logged. Or I don't know if this was a total number, I cannot remember anymore, but anyways, 23,000 methods that had a log, right? So regardless of the number, you can see that there's a big difference between methods that are logged and methods that are not logged. So 7% of those, almost 8% of those are logged. That matches empirical research. Both in open source systems and industrial systems, you see the number of log lines ranging from 3 to 6 or 7%. Then we tried, same thing, binary classification. Let's see if the models learn how to separate between methods that need logs and methods that don't need logs. Again, random forest does a pretty good job, a precision of around 80%, a recall of 60%, a balanced accuracy of 79%. Good thing to notice here is that the number of false positives, meaning the number of times we would say to the developer, there needs to be a log here, and the model would be wrong, is quite small when you look at the big picture, right? Like 1% of the predictions are false positives. Of course, we have false negatives, right? Sometimes we forget to say this model deserved a log, but usually the trade-off we have been doing is we prefer not to bother developers, right? It's our intuition has been that it's better to miss some stuff if it's not a lot of stuff, some stuff. But that's better than bothering developers with false positives because soon they lose trust. We then did more empirical studies to see how those models would react. The data set was imbalanced, right? Only 8% of the methods are logged. That might, you might want to try to balance things to see if the models get better or worse. As always, you see a trade-off there. You get some recall, you lose some precision. Again, for you as an engineer, you got to decide what's more important to you, and then you train your model correctly. I'm not going to dive into what smooth and random undersampling means. We can talk about it later if you're curious. Then we try to understand a little bit about what those models were using as features. What is the important thing for those models? And what we notice is, regardless of the type of the model, meaning random forests, logistic regressions, decision trees, so on and so forth, the number of nested blocks seems to be a very important feature for those models. That makes sense to me, right? More complex models or more complex methods, full of nested blocks, those are the ones where, complex stuff is happening, and those are the ones that you might want to log, right? Of course, it's not causal analysis. Understanding what those models are doing is very hard. No one really knows how to do this, but this gives us a nice insights on what are the important things right now. Maybe in real life, once you want to also make these things into production and sell those, you want to train the smallest model possible, right? So, and maybe, a model with a feature like that would already be, 60% precise, and maybe you can go from there. Finally, we were also curious to see how much this generalizes. So we got lots of projects from Apache. This time we manually picked those, so we wanted projects that use logs properly, right? You don't want to use Apache Commons length because there are no logs there. You want to learn from projects like CloudStack, Hadoop, and etc., right? Where logs are really, key to the projects. So we trained the model on Apache, and we tested in our industry partner. And then the results are not so good. So precision 63%, I'm not going to say that's bad, but recall 25%, that's just awful, right? Which to me means that differently from the refactoring problem, logging is very different from, open source to industry, or from open source to enterprise type of systems. We tried to see if there was one project that would perform better, and CloudStack gets a better performance. So you see a precision of 62, but a recall of 46. So still, okay-ish, but I wouldn't deploy a model like that. So definitely in this problem, maybe what you want to do is to learn from your own data. Cool. Let me see what time this is now. Okay. Then the final paper I want to present before I open to discussion is, or by the way, you can ask me questions at any moment, okay? Learning off by one mistakes. And this was also done together with Ajin by my former master student, Hendrik. And I like to show this paper because this paper shows how deep learning works, right? So far, I was showing mostly machine learning, traditional machine learning, where people have to do feature engineering, you have to think about what to extract from the data. And here, this is more, deep learning. We just give source code and we let the model learn what's important. And the idea was, let's try to train a model that learns to detect off by one mistakes, right? So in a naive way of saying, we want to find places where the developer, instead of making a smaller than or equals to, the developer wrote a smaller than. And there's a bug, for example, in this snippet to kind of illustrate that this is tricky to find. Of course, in this snippet, there's just one place where this bug can actually happen, given this smaller than or equals to example, but in a bigger method that can be tricky, right? So the correct version you can see in my slide. Very small mistake, but we do this all the time. We mined open source systems just have some intuition of how many of those you can find, and definitely you can find a lot of those in big projects. Jenkins, etc., right? And we decided to do that because there was a paper by Facebook published in 2018 where they trained a model that was able to predict whether suppose a method call that receives two parameters, A and B. The model was able to detect if you switch the parameters by mistake, you pass B and A. You're programming in JavaScript, you don't have a strong type checker there. So maybe you can make this mistake or only get those in runtime. And those models could learn and detect those things, right? Mostly because those models end up learning the names of the variables and the semantics of the names of the variables. And that's how this works, right? The model sees that you're passing name and age all the time to the methods. When you pass age and name, then the model, oops, there's something strange here. So we decided to try similar models there. Although I think the off by one mistake is more tricky because it not only involves the semantics of the method, but also the structure of the method, right? That's what we tried. And when you're doing deep learning, the tricky thing is how you're going to represent what you want to learn from into something that can be digested by deep learning models, right? And what we did here was we followed some ideas from the graph neural network people, also, now very popular in software engineering. And the idea is if you have the AST of the method, you can see this as a sort of a graph and a very complex graph. And one way to represent a complex graph is you just do random walks in this graph from one non-terminal to another non-terminal. And you do this, a lot of times. We did it 300 times. And you just concatenate all those random walks, and hopefully this will be a nice representation of the overall graph, right? People that do GNNs, graph neural networks, they showed that this works. So that also works in source code, and that's what we do, right? So that's how we represent. Before I show some more details, let me just say something, which is we need training data. We get data from GitHub. We assume all methods there are correct. They're non-buggy methods. We then insert a bug on purpose, right? So for example, in here, we change this greater than or equals to just greater than. And we give both to the model with the label correct and not correct, and we let the model learn. We used an architecture also proposed by Facebook, which is called Kotovac, highly inspired from Word2Vec, right? Very popular in NLP. And the ideal is each one of those, things here, the blue ones, they are one of those random walks I mentioned. You kind of give those to the model. And the idea is that you're going to learn one vector that is going to represent the code, right? The code vector. Of course, you put an attention layer because we know this kind of works. And the ideal is that this attention layer will learn which of the random walk is more important for the problem. Then we train on the task that is to predict the bug. In the Facebook paper, their task was more complicated. Our task has just one neuron here. And we just, we get a probability of whether there's a bug in the code or not. We tried fancier architectures, the next version of Kotovac, which was Kotosac, basically using sequence-to-sequence models. I'm not going to dive into those. And we tried, 1990s NLP, which is TF, IDF, and then I just give it to a traditional model like random forest. Of course, this is just horrible. We trained on a lot of methods, 1.6 million methods from a Java dataset that is also created by Facebook. Results are very good when things are done in a controlled environment. So we got up to 85% precision, 85% recall, which is really good, right? Can you imagine a model 85% of the times when the model says there's an off by one mistake here, the model is correct? That would be awesome, right? We would never, ever write those bugs anymore. But, when we tried at the company, the results are not so good. You see a very, very, precision is still, okay-ish. 7 out of 10 times that the model says there's a bug, but the recall is very low. So the model misses a lot of the bugs. I would say that's okay, right? You would miss the bug anyways. So you might as well have a model that, 7 out of 10 times when the model says there's a bug, there's a bug. So I would do that. But, then we decided to try this in real bugs, because in here, when we tried at the company, we got all the code base of the company and we mutated, right? So we inserted fake bugs in there and we tried to find from those fake bugs. Now let's try on real bugs, right? Bugs that have happened in first open source systems. So we manually collected 41 of those bugs plus 41 fixes, so 82 things, and we used our model to see if the model would detect those things. And the results were just awful, right? Just a little bit better than, random guessing. So not very good at finding real bugs. We also tried this at Agin. We got the latest version of their code base. We set our model to only report bugs for us if the model was 80% or more confident about it, because we don't want to have a lot of alerts. Out of the 7,000 methods that could have contained such a bug, there were 36 alerts, which we then got a developer and we said, review all those 36 methods. The developer at the end of the day did not find the bug. It could be the developer could not find the bug, but you never know. So according to the developer, there was no bug in there. But in 7 cases, the developer said, well, this is really strange, really strange. We should not program like that, right? And this actually matches findings from related papers. Because one interesting thing is that those models not only learn the task that you wanted to learn, like finding bug in this case, but it also learns your coding style. Let me give you an example. So in those 1.6 million methods we collected, whenever there's a for loop, 90%, I'm guessing 90%, right? A very large number of for loops are written like this: I equals something, I smaller than something, right? Only in a small number of cases, the developer actually does I smaller than or equals to something. Both are the same, right? But developers definitely prefer smaller than, not smaller than or equals to. That's what we see in the wild. And so at the end of the day, the model learns that whenever there's a smaller than or equals to, wow, this is a rare thing. Developers don't do this. So maybe that's a strange thing, right? Because whenever I see this, odds are that there's a bug. So the model starts to learn your coding style. And that's kind of a big issue for all this type of work, because coding style matters, right? That those models are learning those things. So at the end of the day, this is a model I don't think we can deploy right now. In contrast to the other two, which I think companies could already get some benefits, but this one, yeah, we need to do more research. We need to fine tune it a little bit more. Just to give an example of how our tool that we created at the end of the day looked like. So this is the method. We're going to insert a bug here. We're going to ask the model to detect, and then we create the visualization here, basically the AST, and then the color indicates where the model is looking at to detect the bug. And you can definitely see that the model is paying attention to the for loop and to the comparison in the loop. So those models are kind of learning where to look at, right? They are not so stupid. They know, given a method, where to look for those bugs, but they are just still not very good. But maybe, in a few years. Cool. Then let me switch to the end of my presentation. Did I cancel my screen sharing? I guess so,
Yes.
right? Let me share again. Great. So final words, just so that I can convince you that this is possible to be done by anyone. And so first lesson is that machine learning seems to be an interesting solution for many of the problems that I at least care about, like code quality and help developers take maintenance decisions, testing decisions. So I think machine learning will definitely be the future in this type of, in this area, right? I'm pretty sure we're going to use SonarQube because it contains rules that were created by humans and we like those. And those tools will be complemented by machine learning models that actually learn from the way you and your company program. A lot of those ideas, for example, my off by one mistake paper, they look good when you try those in controlled environments. Results are good, but when you deploy or when you try in a more realistic task, results are not so good. So I think there's still a way or a long road for us to do before those models are there for everybody to use. But we are getting there, right? We are definitely getting there. big companies like Facebook and Google are trying this. Facebook in particular has a huge team nowadays that only does this, train models for their internal use in all sorts of stuff, like predicting whether a test is a flaky test or not, given a new pull request, what tests should they run first, because Facebook cannot run all their test suites whenever someone does a change, so prioritizing test cases is an important problem, so on and so forth. Generalizability, at least to me or to the problems I'm working on, sounds like a little bit of, it's just overrated. My results show that training models that learn from your code base, they just perform better. Yeah, of course, this is only possible. This might not be possible for deep learning approaches. Those require millions and millions of data points, which you probably don't have. But machine learning techniques, more traditional ones, can learn from less data points. The disadvantage is, of course, those models cannot learn very, very, very super complex problems, right? Like maybe finding bugs. I would never try a traditional machine learning approach to find a bug. But refactoring, for example, that might work. Also, something that we need to find a way is that developers simply do not trust magic stuff, right? We have deployed those things in different companies, in the 2 industry partners we have, not as a real production tool, but many times we showed stuff to developers. And it's pretty hard for them to trust the magic stuff, right? They see the recommendation, but they say, can you explain this to me? And they simply don't trust because this comes from a black box. We will have to find ways to present this information, or at least a little bit of explainability there. Also, I think what happens is developers are not really trained in machine learning, and even less so in machine learning for software engineering nowadays. So I think this at some point will be just part of any software engineering program, understanding how those models are trained, right? Because I'm pretty sure if I explain to you that these models are learned from these characteristics of your code, the recommendation will start to make more sense to you. Finally, do not let anyone tell you that if you don't have a PhD in machine learning, that you should not be doing machine learning, right? This is just pure gatekeeping. Of course, I'm not saying you don't have to learn machine learning. Of course you do if you want to do, sound stuff, but you definitely don't need a PhD on the topic, right? So I'm a computer scientist. I have a PhD in software engineering. I know machine learning, but I'm definitely not an expert. I have been studying this for a long time. I can understand most of the papers in my area right now. But if you give me a paper, a theoretical paper on machine learning, I might understand 50% of it, but that's okay, right? Because what I'm trying to do here is applied machine learning. I get those ideas, I try on my domain, I see the results. And that is possible for anyone to learn, yeah? So do not be scared about machine learning. I showed a lot of crazy stuff, right? I said lots of terms you might not be familiar with, but if you study, very soon you're gonna learn the intuition behind all those things. And you can do it, right? Do not be scared by all the mathematics you see on the papers. Machine learning is a mathematical thing. Those formulas have to be there, but it's okay. Let the theoretical people do that, and we do the applied stuff. At least that's what I'm thinking right now. That was my presentation. I hope you could get a grasp on what machine learning for software engineering means and where the area is heading to. Questions, remarks, tell me.
Hey everyone, someone have any questions for Mauricio? Don't be shy.
Hey, this is Sarkam. I have a question. Do we have any numbers that represent the required size of a code base to benefit from these tools?
Good question. I think there are two things. So one is, if you have a trained model, then it doesn't matter the size of your code base, right? You give me a method, I will give you a prediction. So it doesn't matter. It can be small code base or a big one. But if you want to train a model on your code base, you need to have data points. And it's pretty hard to know how many data points. The more data points, the better, right? Because the more nuances those models can learn from. But our paper at ING, for example, we show that with 2,000 data points, you get good models already, right? So it's not a lot. It's not a lot. For the deep learning models, there we're a bit screwed. You really need millions and millions of data points. And there, like for example, GitHub Copilot will never work. It cannot be trained on your company, right? You have to train on millions and millions of stuff.
Okay. That makes a lot of sense. Thank you.
You're welcome.
Hey, Mauricio, by data points, we are talking about like methods, total of methods or total of classes. Those are the data points?
It depends on the problem you're trying to solve. So for example, in the refactoring model that I showed, a data point is one refactoring. So your code base has to have 2,000 extract methods in the history, right? Those are what I'm talking about. In the logging one, it's just, the number of methods you have with logs and without logs.
Another question from me, if I may.
Sure.
So if you wanted to experiment with this internally, would you prefer we start with AST, like transforming the code to ASTs first? Or do you think it's okay to start out with the text representation of the code?
Yeah, so I think if you were to start right now, so my suggestion is to use the models I presented here, right? So the ones that are based on traditional machine learning, which are mostly code metrics. And you don't have to do anything. You can just run our tool. You just give, the URL of your Git repo to the tool, and the tool will do the magic for you.
Okay, magical. Thanks.
Yeah, a lot of source code does all this magic for you. And then a lot of Python code trains the model. What we don't have right now, or we actually do, but it's not so easy to use. We also have a tool that gets the model and gives the recommendation at code review time. So if you have like GitHub or GitLab, whenever there's a PR, we make a comment for you there. But that one, yeah, it's not very flexible. So maybe there you would need to customize for your company a little bit and maybe submit a PR back to us. So that
all right. Okay.
I see a question by Isela. What is the difference between deep learning and machine learning? So that's a very good question. I'm going to give you my answer. Maybe if you ask someone from more theoretical machine learning, the answer will be different, right? But when I'm talking about machine learning here, I'm mostly talking about the type of machine learning you do when you model the features as a person. For example, in the refactoring problem, as a machine learning engineer, I thought, let me give to this model features like the complexity of the code, the number of lines of code, so on and so forth. So I decide the features, and I hope that those features are good enough for the models to learn. So this is more traditional machine learning, right? Deep learning, on the other hand, the ideal is you don't even do that. You just give raw stuff to the model, and you let the model learn. So they just give source code to the model, right? And of course, this is just much more tricky. You're not giving tips to the model. And so for the model to learn, you need a very deep network. You need, billions and billions of neurons trained on top of a lot of data for that to happen. Deep learning is very common, for example, in computer vision, like those self-driving cars, for example, they use deep learning. So in software engineering right now, you see a little bit of both. And I usually try machine learning first because it's simpler, it's cheaper. If that doesn't work, then I go for deep learning.
Okay, I have one more question. Apologies for like shooting questions.
No,
okay, all right, thanks. So have you ever tried analyzing actual GitHub pull request conversations rather than commits? Because usually commit histories are squashed, but PRs seem to contain opinion of those developers as well, comparing what looks better incrementally.
No, and that's definitely a point to improve. So right now, I just get any refactoring in your repo. I don't care why you refactored, and that might be a problem, right? Because maybe that refactoring was not relevant. You just did it because you had nothing to do, and maybe you just want to learn from refactorings that are important, or maybe something that other companies have been asking me. Maybe the type of recommendations you need when the project is starting is different from when a project is more mature. So maybe I think the future will be, we will get better at data collection, right? And then, so maybe you can train different models for different situations. Maybe we can learn from the PRs and the discussions, right? If the developer says, this is the best refactoring ever, that's a good point. That's a good data point. If the developer says that refactoring sucks, roll it back. You don't want to learn from this. So
also, a lot of refactors actually happen within the PR, which is not reflected in the actual commit that's merged back.
Yeah, exactly. So maybe you miss all those things because when you squash things, maybe you lose information, and then extracting the precise refactorings, it's tricky. There are lots of things to improve. And in machine learning, people say garbage in, garbage out, right? And I think the future will be that we need better tools to do data collection.
Yeah.
Yeah, I think we are a little bit over time. So thank you so much, Mauricio. It was very nice presentation, very bringing the academic researching for industry in a very practical way, I think. As always, you explain very well. And yeah, thank you.
My pleasure.
Thank you, everyone.
My pleasure. Enjoy the rest of your day. Enjoy your night.
Thank you so much, Mauricio. Really, thank you.
Yeah, thank you.
My pleasure. Bye.
Thank you very much. That was
everyone.
cool. Really cool. Bye-bye.